However, it is reasonable to suppose that the amount of this unobservable matter is not so very much greater than the amount of the observable matter. We get for the total number of nucleons in the universe a number around 10 to the power of 78. According to our large numbers hypothesis, this must be increasing proportionally to the square of the age of the universe. The total amount of matter is increasing proportionally to the square of the age. That means that new matter is continually being created. Now, cosmologists have been talking a good deal about continuous creation of matter in connection with the steady state theory of the universe. Well, the steady state theory is rather discredited, and I'm not going to make use of it at all. I'm working with the Big Bang model of the universe, according to which the universe started off at the time 10 to the 39 in the past. But even with this Big Bang model of the universe, we need continuous creation of matter. The continuous creation of matter is a necessary consequence of the large numbers hypothesis. Now, if we have matter continually being created, we are faced with the question of where is it created? There are various assumptions that one might make. I will list three of them. Assumption A: the new matter is being continually created uniformly throughout space. In that case, it is mostly created in the intergalactic space, the space between the galaxies. This is assumption A, uniform creation. Then there is assumption B: matter is created where it already exists in proportion to the amount existing there. Thus, there's no matter created in the empty space between the galaxies. This is where it already exists. Then one might make a third assumption, that new matter is created just in certain special places, such as the centers of galaxies. I don't know which of these hypotheses to prefer, so we must bear in mind that either of those may hold or may be something quite different. Let us examine the consequences of those different hypotheses, and let us apply it to a very simple example: the motion of the Earth in its orbit around the Sun. Using just the Newtonian approximation, we have this formula: G, gravitational constant, big M, the mass of the Sun, is equal to v squared r. V is the velocity of the Earth in its orbit, r the radius of the Earth's orbit. This follows at once from elementary Newtonian mechanics. Now, this equation should hold whatever units one uses. It must hold if one uses the Einstein units, and in that case, every one of these quantities is a constant. The equation must also hold if one uses atomic units. In that case, these things need not be constant, and we should have this formula: GA MA equals BA squared RA, where these things refer to measurements made in atomic units. Now, VA, the velocity of the Earth in its orbit, is a certain fraction of the velocity of light. That is dimensionless. It must be the same whatever units we use, so that VA is the same as this V. It is a constant. Now, GA is proportional to t to the minus 1. Let us write down these results. GA is proportional to t to the minus 1. VA equals constant. Now, Ma, the mass of the Sun, is a constant if we make either of these assumptions A or C. On the other hand, if we make assumption B, that matter is being created where it already exists, then matter will be created in the Sun. And with assumption B, Ma will be increasing proportionally to the square of the time. With assumption B, all matter must be multiplying at the rate proportional to t squared. So we have these results with A or C, Ma equals constant. With B, Ma is proportional to t squared. Now, substituting in this formula here, you see that with Ma constant, Ga proportional to t to the minus 1, Ba constant, we get Ra proportional to t to the minus 1. And with assumption B, Ra is proportional to t. If we use assumption A or B, it means that the radius of the Earth's orbit is contracting, and the whole system of orbits in the solar system must be contracting in the same ratio. With assumption B, on the other hand, there is a whole expansion of the Earth's orbits and of the whole solar system. These effects are very small, and we don't know whether they are right or not, but in a few years' time, we shall know from Shapiro's observations, and then we shall be able to check out whether we have this formula, or whether they're both wrong. With this assumption A or C, we have the radius of the Earth's orbit varying like this, and all distances measured in atomic units must be varying in the same way. dSA is proportional to t to the minus 1 dSE. While with assumption B, dSA is proportional to t dSE. We have thus this connection between the two dS's, depending on which assumption we make concerning the creation of new matter. In either of these cases, we have a difference between dSA and dSE, and that suggests another development that we might make in our ideas of space and time. Let us bring in the electromagnetic field. That involves forces which fall off inversely proportional to the square of the distance, just like gravitational forces. There is a close similarity between the electromagnetic field and the gravitational field, and that has led people to believe that they must be closely connected, and as the gravitational field can be explained in terms of geometry, one would think that the electromagnetic field should also be explicable in terms of geometry. That has led people to look for some more general geometry than the Riemann geometry, which will account for both of these fields. People have been hunting for this more general geometry ever since Einstein's theory was first proposed. This hunt is called the search for a unified field theory, the unification being the unification of the geometrical and the electromagnetic field. Now, very soon after Einstein's theory was proposed, Weil proposed a method for unifying the two theories, the two fields, by setting up a more general kind of geometry. I would like to explain the main idea of Weil's geometry. One can do that with the help of the notion of the parallel displacement of a vector. We have a vector located at a certain point. We shift it, keeping it parallel to itself. Now, we may go on shifting it, keeping it parallel to itself, following along some curve. And we may take the curve to be a loop so that we end up with the vector located at the same point where it started from. But the direction of the vector may have got altered when it is shifted around the loop. If the space is curved in accordance with Riemann's idea, then we shall end up with a different direction from what we started with. You have a very simple example that if you take vectors on the surface of the Earth, shift them round like this, when you get back to your original position, the vector will be in a different direction. And that is why the three angles of a triangle, when the triangle is marked out on the surface of a sphere, do not add up to two right angles. The curvature of space can be interpreted as a change in the direction of the vector when we move around a loop. Now, Weyl's generalization was to suppose that the length of the vector also changes as well as its direction. That is a perfectly natural generalization for a mathematician to make. However, that generalization did not suit the physicists, because you may suppose that the length of the vector is always referred to atomic units, and then the vector referred to atomic units may keep the same length, and there will be no change in its length when we go around a loop. So that Weyl's geometry, although it was a very nice mathematical idea, was not accepted by the physicists. However, with the general ideas that I've been talking to you about today, we see that the length of a vector measured in these units referred to dSA has to be unchanged when we go around a loop, but it could very well be that the length referred to dSE does change. We can set up a theory on the basis that we have Weyl's ideas referring to dSE. The ratio between dSE and dSA is not exactly given by these formulas here, but just approximately, and that there is a sufficient freedom in this factor here to allow dSA to remain unchanged when we move by parallel displacement around a loop, while dSE does change. Well, I told you how Weyl's theory was not accepted by physicists when it was first proposed, about 1919, and Weyl himself saw the force of the physicists' arguments, and he abandoned it soon afterwards. People have been searching since then for other means of unifying the gravitational and the electromagnetic fields. They have not been successful in finding a satisfactory solution of the problem. Einstein himself spent many decades just trying to solve that problem without success. Well, I want to propose to you that this problem of the unification of the electric and magnetic fields is to be made like this, applying Weyl's ideas to dSE and recognizing that dSE is not the same as dSA. Well, I would like to perhaps say a little about the mathematics of Weyl's geometry. I won't go very deeply into the equations. With Weyl's geometry, we take a length L and shift it by parallel displacement from one point to a neighboring point. It will change by an amount dl proportional to L and also proportional to the amount that we change the coordinates by, the dx mu which we have there. And then we need some coefficients kappa mu occurring there. Now dl has a definite meaning only if we set up artificially a metric gauge at each point in space and refer the length of our vector to this metric gauge. We might change the metric gauge by some factor lambda. The metric gauge is quite arbitrary, we can change it by a factor, let us say a factor lambda, which varies from one point to a neighboring point. And then if we do that, we can easily work out that the change in kappa mu is like this. Kappa mu goes to kappa mu plus d log lambda by dx mu. The kappa mu's are subject to these transformations where lambda can be quite arbitrary. And this reminds you of the electromagnetic potentials. The electromagnetic potentials have an uncertainty in them, just expressible by the same formula that we can change the kappa mu's by the gradient of some scalar. And thus we can identify the kappa mu's occurring in vase geometry with the electromagnetic potentials. The generalization of passing from Riemann's geometry to vase geometry just brings in certain coefficients kappa mu, which can be interpreted as the electromagnetic potentials, and thus that provides us with just what we need to bring in the electromagnetic field together with the gravitational field. The kappa mu and the g mu nu now occur together for the description of the geometry. They both occur on the same footing, and they are needed to describe the gravitational and the electromagnetic fields together. In developing the theory, we have to set up an action principle in which we have some quantity for the action which is invariant not only under changes of the coordinates, but also under changes of the metric gauge like this. These are called gauge transformations. There is a little difficulty in finding a suitable action integral. Weil himself noticed difficulty, and he set up quite a complicated action integral, far too complicated to form a reasonable theory to work with. I would like to propose a different action principle from Weil's, which brings in another scalar field quantity for describing the gravitational field, in addition to the g mu nu's. This theory of mine is somewhat similar to a previous theory proposed by Brands and Dickey. They also introduce a scalar field as well as the g mu nu field for describing gravitation. But the development of my theory is not the same as Brands and Dickey, because Brands and Dickey do not have invariance under this kind of transformation, which is demanded according to the ideas which I've been expressing to you. Well, I don't think I can go more into these mathematical developments, but I would like now to refer to one striking feature which arises when we introduce this Weil geometry and accept that as the geometry of physics. This is concerned with the symmetry properties of space and time. Let us discuss a simple example. Suppose we have a charged particle and we take a field point near this particle. Let this be the world line of the particle, this being the time direction and this being the space direction. Time direction one usually calls it x0, and this would be x1, 2, or 3. We take a field point here. Let us imagine that we have a system of axes for which the particle is momentarily at rest or approximately at rest. Let us take a vector at this field point and shift it into the future. That means we shift it like this. We ask how the length of this vector changes. That is given by this formula here. dl over L equals kappa naught dx naught. We are shifting it into the future so that dx naught is the only one of these dx's which doesn't vanish. We consider this particle to be charged so that the potentials near the particle will be dominated by the Coulomb potential arising from the charge. We may suppose that the charge is such that kappa naught here is positive. That would mean that dl over L increases as we go into the future. Alternatively, we might change the charge here. We would get kappa naught negative. We would have dl over L decreasing as we move into the future. Now, there is no symmetry between a quantity increasing and the same quantity decreasing. They're two fundamentally different concepts. So that we have a geometry in which there is no symmetry between positive and negative charge. Alternatively, we may consider shifting into the past. Now, if dl over L is positive when we go into the future, it is negative when we go into the past. There is no symmetry between future and past. Suppose we change both the sign of the charge and make the interchange of future and past. Then we get back to the original situation. Now, atomic physicists have introduced certain operations describing these symmetry processes. They have the parity operation, P, which involves passing from a left-handed system of axes to a right-handed system of axes. Then they have the operator of charge conjugation, denoted by capital C, which involves interchanging positive and negative electric charge. And they have T, the operator of time reversal. According to the geometrical ideas that I have been giving to you, we see that there is no invariance when we change C, there is no invariance when we change T, but there is invariance when we change P. This geometry does not get affected with the interchanging of left and right system of axes. So that we have a geometry in which P is conserved, also the product CT is conserved, although C and T separately are not conserved. Now, experimentally, it is observed that all three of these operations are not conserved, although the product PCT is conserved as far as we know. The Weil geometry goes some way towards explaining that situation. It does not explain the violation of P. That must come from some other effects which are not brought in by this geometry, and they may be concerned with the short-range forces of atomic physics. However, the geometry does explain violation of C and T while preserving CT, so that we go some way towards getting to the situation that we want in connection with these symmetry operations. That is a striking feature of the Weil geometry, which does not occur with other geometries. The other geometries all have conservation of P and of C and of T, and they go nowhere at all towards explaining why some of these are violated. Well, those are the ideas that I wanted to present to you, and perhaps I should conclude by considering the question, why should one believe in these ideas? In the first place, these ideas require G to vary with the time. We may hope within a few years to get a very definite answer from Shapiro or from Beams as to whether that is true or not. I feel very strongly that it must be true because I cannot see any other explanation for the large numbers. Now, even if it is established that G does vary with the time, we will still not have proved Weil's geometry. Weil's geometry is a further assumption which seems very reasonable and plausible, but the effects are so small that it would be difficult to check it by direct observation, except possibly in connection with these violations of symmetries. But there is one reason why one feels very much in favor of Weil's geometry. It seems that the laws of nature have to be invariant under a wide group of transformations. The reason why Einstein's theory is so popular, so much accepted, is that it sets up a much wider group of transformations for the laws of nature than we had previously, namely the group of all transformations from one curvilinear system of coordinates to another. That, I believe, is perhaps the dominant reason why Einstein's theory is so favorably received. Now, Weil's geometry goes a step further in the same direction. It sets up a still wider group of transformations under which the laws of nature have to be invariant, and that would seem, according to the whole development of our physics, that it should be really the way in which nature works. Thank you.